In this video, we'll be talking about common and natural logarithms. But before you continue on with this video, please make sure to have at least 3 different colored writing utensils. So please pause this video and hit play to resume when you have all necessary materials. Now, the past week we've been studying exponentials. So how do exponentials relate to logarithms? Well, they are inverses of each other. In math, it is typical that you learn how to do a method one way and then you learn how to undo it, just like with adding and subtraction. Here we're going to learn logarithms and how they undo exponentials and how we can use exponentials to undo logarithms. Let's take a look at the relationship between an exponential function and a logarithmic function. So here's where you'd want to use your different colors for writing to copy down the relationship between an exponential function and a logarithmic function. Notice the use of the colors and the placement of the values or the variables. When you're using a logarithm, what you are doing is you are finding the power or the exponent that the b value needs to be raised to. So let's take a look at an example, okay? And so the first example is going to be 2 to the third power. Now 2 to the third power equals 8. Now this is an example of an exponential function and how we can easily rewrite this into a logarithmic form. So looking at this, I'm going to change my colors so that the 2 is in green because it is the base of that exponential. I'm going to change the 3 to be in blue because that is the exponent. And I'm going to change the 8 to be purple because that is my y value. By changing these colors, it's going to help me rewrite my logarithmic function. So the first thing that I need to do is take my exponent, which is 3. I'm then going to set that equal to the logarithm of base 2, because I need my b value, my base of my y value. Now, when you're writing the base for your logarithm, please make sure that it is a subscript notation, so it's written smaller and lower in comparison to log. Let's take a look at another example. Here we have 5 to the 4th power equals 625. Now again, we're going to change the colors so it matches our relationship up top. So I'm going to need to change that 5 to green because that is my base of my exponential function. And the 4 is my exponent, so that needs to be changed to blue. And then the 625 is my y value, so that's going to be changed to purple. Now, in order for me to rewrite this in logarithmic, in a logarithmic notation or for in a function, I'm going to start with my exponent, which is 4. I'm then going to set that equal to the log with my base as a subscript, so my base is 5. Of what it equaled, so 625. Now let's take a look at one that would be written in logarithmic and change it into an exponential function. So let's write log base 3 of 81 equals 4. So what I'm going to do is put my base in green, and then the 81 is my y value, so that's going to be written in purple, and then the 4 is my exponent, so I'm going to change that to blue. So really what this is saying is my base 3, if I were to take that and raise it to the 4th power, that would equal 81. So what I'm doing is I'm finding the exponent, or I'm finding what power I would have to raise my base to in order to equal the y value. Let's try one on your own. So on the left-hand side, I would like you to take this exponential function and rewrite it as a logarithm. And then I would also like you to take this logarithmic function over here on the right and rewrite it as an exponential. Now, there are two different types of logarithms. There's the common logarithm and there's the natural logarithm. Now, the common logarithm is a log that has a very specific base of 10. So it's log base 10 of x, or sometimes you're just going to see it as log of x. So assume that if you see log of x, that it has a base of 10. It's just one of those things that as mathematicians, because we write it so often, we tend to forget our base. Okay? The other thing is a natural logarithm. Now, a natural logarithm is a log with a base e, and we talked about that in our previous ed puzzle, what e represents. So, anytime you see the natural log, know that it's a log, a common log with a base e. And it's one of those things that, again, because we write it so much or we use it so much, we ended up making it have a very specific and its own logarithm. So it's a natural log. Now, why it's ln instead of nl, I don't have the answer to that, but just know that that's natural logarithm. So we're going to take a look at some examples to understand and have a better relationship with this. So before we begin our examples of common log and natural log, let's just review the relationship between an exponential and a logarithm. So if we have base b raised to the x power, that's going to equal y. So if we transfer that now to a logarithm, it's basically going to say log base b of y is going to equal x. Okay, so we're going to solve for that exponent. So let's take a look at an example where we would need to use the natural log. Okay, so we want to make sure that our problem has a base of e. So here we go. E to the x power equals 9. There's our first example. So if I'm rewriting this, I'm going to say that it's the log base e of 9 equals my exponent. Now, the issue is this log base e. That's not something you're going to see. What you're going to see is a natural log of 9 equaling x. That's what you're going to see. You won't see it written with the common log and a base of e. Let's take a look at another example. What if we started off with a logarithm? So a log of 1,000 equals 3. Now remember, as mathematicians, we don't always write it, but there's that base there that has a base 10. So if you don't see any subscript, assume that it is a base 10 if it's the common log, or it's base e if it's the natural log. So now let's take this log of 1,000 equaling 3, and let's rewrite it as an exponential. So I'm going to start by writing my base, which is 10. I'm going to raise that to my exponent, and that's going to give me an answer of 1,000. Let's try another example. Here we have e to the 9th power equals 8,103 and 8/100. If we were to rewrite this in logarithmic form, we're going to start off by writing log with my base of e of 8,103 and 8/100. And that's going to be set equal to my exponent. Now again, remember, we don't write log base e. We write the natural log. So really, my final answer would say the natural log of 8,103 and 8/100 equals 9. Now, I'd like you to try some on your own. So here are 3 that I want you to try on your own. The 2 on the left are logarithms, and I'd like you to rewrite them as an exponential. The one on the right is an exponential, in which I'd want you to write it as a logarithm. So there are some properties with logarithms that we can use, and it's best to understand those properties when we can change them into exponential form to see where they've come from. So if we take a look at the left side, we have log base b of 1 equals 0. Well, really what that is saying, if we transfer that logarithm into exponential form, is b to the 0 power equals 1. And we know that anything raised to the 0 power is going to equal 1, no matter what that base is. Now the second logarithm, log base b of b equals 1, is saying that b to the first power is going to equal b. So really what that is saying is 4 to the first power, well, that's going to be just 4. Now the last one is log base b of b to the x power is just simply going to equal that exponent. What that really is saying is b to the x power is simply going to equal b to the x power. So therefore, we can conclude that our exponents have to be equal because our bases are equal. That is why we can say it's just going to simply equal x. Now these properties apply too when you're working with the natural logarithm. So here I've given you the exponential form, and we're going to transfer them into the logarithmic form using the natural log. So this first one is saying e to the 0 power equals 1. So really what that's saying, if we transfer it into logarithmic notation, is the natural log of 1 is going to equal 0. Now if we take a look at the second exponential form, here it says e to the first power equals e. If we transfer that into natural logarithm form, here's what it's going to look like. It's going to be the natural log of e equals 1. The third exponential function here, e to the x equals e to the x. If we transfer that one into logarithmic form, here's what that one would look like. Natural log e to the x power is simply just going to equal x. Now let's use these properties to our advantage, going back from exponential to logarithmic form to simplify. So the first example I'd like to show you is this one, where it has a log base 4 of 16. Now, one way to look at this is by first examining 16. Now 16 is simply 4 squared. Now the reason why I'm looking at it exponentially is because logarithms undo exponentials. Okay? The second reason why I'm looking at 16 as being 4 squared is because they both have a same base of 4. So what I can do is instead of writing 16, I can write this as being the log of base 4 of 4 squared instead of writing 16. Now this reminds me of a property that we just examined where it was log base b of b to the x power and how that simply just equaled the exponent. And so it just is going to simply equal 2. Now you can't do this on your calculator because your calculator will only do natural log and common logs. So that's why we have these other properties to be able to answer these types of questions. Let's take a look at another example. What about if we had log base 5 of 5? Well, really, I can think of that as 5 to the first power. So instead of writing this as log base 5 of 5, I can write this as log base 5 of 5 to the first power. Then again, it is just like this property here, where it's just going to simply equal 1. You could have also used the other property, log base b of b, and how that equals 1. See how you would answer this question. Log base 3 of 27. Again, kind of use the same thought process that I explained in this log base 4 of 16.